A sample of gas can be described by four variables: its pressure, its volume, its temperature, and also the number of moles or molecules of gas inside the sample. We will be abbreviating moles with a lowercase n. In this video, we're going to be looking at three laws: Avogadro's law, Charles's law, and Boyle's law. These laws give us relationships between any two of the four variables of a gas. So we'll be starting with Avogadro's law. Avogadro's law gives us a relationship between the moles of a gas and the volume of a gas. And it is important to point out that Avogadro's law only applies under conditions of constant temperature and pressure. So this is some sort of situation where we're changing the number of moles or the volume of a gas, but the temperature and pressure are not changing. And a good example of the application of Avogadro's law is just blowing up an empty balloon. So this is something that we've all done before. Imagine that you are blowing up a balloon. As you blow up a balloon, are you increasing or decreasing the number of moles of gas inside the balloon? Well, as you know, as you are blowing air into the balloon, and air is gas, you are increasing the number of moles of gas that are inside the balloon. Also, from personal experience, you know that as you blow up the balloon, the volume of the gas is increasing as well. This is pretty intuitive, pretty simple stuff. So increasing the number of moles of gas causes the volume to increase as well. And this gives us Avogadro's relationship. When the moles of gas increase, what happens to the volume? Well, as we know, and like I said, this is pretty intuitive, increasing the number of moles of gas is going to cause the volume to increase. Or vice versa. If we decrease the number of moles of gas, the volume will decrease. So we could say the same thing down here. That is not how you spell decrease. Decreasing the number of moles of gas causes the volume to decrease. So like I said, this is a pretty intuitive relationship, and I think you'll find all of the gas law relationships are pretty intuitive. Let's look at the next one. The next one is Charles's law, and Charles's law gives us the relationship between the temperature of a gas and the volume. And for this, we're going to require that pressure and moles stays constant. So this would be an example of taking a sample of gas and cooling it down. This might be something that you experience with your car tires or your bicycle tires in the wintertime. As the temperature drops, what happens to the volume inside your tire? We're going to be imagining in this situation a balloon. The balloon that we blew up here in this problem right here. Let's take that balloon and let's put it in the freezer and imagine what might happen. If you put the balloon in the freezer, what happens to the temperature? Well, this, of course, is pretty intuitive. The temperature will go down because you've put it into the freezer, so this will decrease the temperature. As the temperature goes down, think about what you know about like car tires or bicycle tires. As the temperature drops, volume decreases as well. And so what's the relationship that we're looking at here? As temperature decreases, decreasing temperature, this causes a decrease to the volume. Or vice versa, if you increase the temperature, this will also cause an increase in the volume. If you've ever gone to pick up a balloon bouquet, like maybe from Party City, and a hot summer day, and put it in your car to drive home. Your car is super hot. Some of the balloons pop on the way home because as the temperature increases, the volume increases, sometimes too much, and the balloon breaks. The last relationship that we're looking at is Boyle's law. Boyle's law gives us a relationship between pressure and volume. And this is under conditions of constant temperature and constant moles. This one's going to be a little bit harder for us to visualize. We don't have a lot of everyday scenarios of Boyle's law, but we're going to imagine that we take this balloon out of the freezer, the balloon that we put up in the freezer up here, let it warm back up to room temperature, grab the balloon with our hands and then just squeeze it. So we're basically compressing the balloon with our hands, which would be really difficult to do. But imagine that you would try to do that. Imagine holding a balloon in your hands and then just kind of squeezing down on the balloon and trying to smash it into a smaller volume. What you're doing here is you're trying to decrease the volume of the balloon. When you squeeze the balloon, if you were to do it successfully, you would be decreasing the volume of the balloon. Now, if you can imagine doing that, because we've all held balloons in our hands, if you could imagine what it feels like to push down and squeeze down on a balloon, there's quite a bit of resistance there. It's not something that happens very easily. Imagine what it would feel like when you're squeezing this balloon. The balloon gives up quite a bit of resistance, and this is because the pressure is increasing inside the balloon as you are attempting to decrease the volume. So as the balloon gets smaller and smaller and smaller, but the gas molecules don't change, the number of gas molecules don't change, and the temperature doesn't change, as the volume gets smaller, there is no choice but to increase the pressure. So for this relationship, as we decrease the volume, this causes an increase in the pressure. And vice versa. If we increase the volume, this would cause a decrease in the pressure.